So again, section 2.4, it kind of started to ease us into hypothesis testing in an informal way. Now we're going to jump to section 10.1 and make that hypothesis testing a little more formal by stating the hypotheses and actually finding test statistic R and a p-value associated with it. So as it turns out, this is the second most heavily tested section in Homework Set 7. So we're going to take a look at a few issues here. We're going to discuss the differences between the sample and population correlations. We're going to set up the hypotheses, and then we're going to let StatCrunch do all the number crunching for us. And then, of course, in the end, we'll have to interpret it. So, all right, samples and populations. So we've been referring to this coefficient of correlation, and we've been calling it lowercase r. And that is, strictly speaking, what it's called when it describes the correlation within a sample. And so far, in the examples we've been using, we've been taking samples, so that makes sense. Now, of course, we would be assuming that this sample represents a larger population that has some correlation throughout that we obviously wouldn't know, but we symbolize it with the Greek letter rho. Rho, it kind of looks like a rounded P. Here's a better look at a rho. But it's actually Greek for R. So I suppose that's why it's used in association with this letter R. All right, so can you remember that? The coefficient of correlation for a sample is called R, but for the whole population is called rho. So obviously we're going to have R in our hands because it comes from the sample that we've observed. And now we're going to try to use this number to figure out what we can infer about rho. So the hypotheses, the null hypothesis, is the working assumption that in the population there is no correlation between X and Y. And this is consistent with everything we've done with null hypotheses. The null hypothesis always has some kind of a no or none or nothing in it. For example, no difference, or no, in this case, no correlation. So in using statistical symbology, we would write that this way. The null hypothesis states, or H0 colon, that the population correlation is 0, rho equals 0. And again, null hypotheses pretty much always use an equal sign as well. Okay, so the alternative hypothesis would state the opposite conclusion. In the population, there is a correlation between X and Y. And that is symbolized by saying that rho is not 0, because remember, if there's a correlation, it can be either positive or negative. So for that reason, this hypothesis test is always two-tailed. We want to find out if rho, the population correlation, is just 0, or if it's not 0, which means that it could be either positive or negative, significantly large or significantly small, two-tailed. Now that being said, StatCrunch will do all the number crunching for us, and we're going to run through an example in just a moment. It's going to show us both R and the p-value. So let's take a peek. Here's the example, and we're going to continue working with that call center. So this is just a copy of the data we looked at before. 9 call centers, number of representatives, hold time for their calls. And I've also copied this table for critical values of R. And we're going to test the hypothesis that there is a significant correlation between X and Y in this example. The first part of the question states, state the hypotheses in English and statistics symbols. So when you refer back to your lecture notes, and as always, of course, if you want to pause the video and make sure that you can answer the question correctly before the big reveal, don't be shy about doing that. You can take all the time you want. I won't go anywhere. But let me talk you through how I would answer the question. All right, so the hypotheses in English. The null hypothesis, again, states that X and Y throughout the population are not correlated. No correlation between them. And then the alternate would be, well, actually, yes, there is a correlation. So we might express the hypotheses in English something like this. Null hypothesis. Throughout the population of all calls, X, the number of representatives, and Y, the number of minutes, are not linearly correlated. Whereas the alternate would be, they are correlated. All right, now to express this in statistics symbols, of course, we abbreviate null hypothesis with H0, and then throughout the population, the correlation would be that Greek letter rho. So if X and Y are not correlated, rho would be 0, and alternately it would not be 0. Now, of course, we can just copy this abstract symbolism for pretty much every problem of this type, but my concern, of course, is that if students just get in the habit of copying and pasting, they're not practicing and developing their connections. So it's really important to me that you really understand exactly what this stands for in this specific problem. The next part of the question says, use StatCrunch to calculate R and its p-value. We haven't done this yet. Here's something new. Let's go to StatCrunch. And if you look at your lecture notes, this tells us that we're going to go to stats, summary stats, and correlation. Okay, well, I guess it's stat, not stats. Stats singular, summary stats plural, correlation. Select the columns, representatives, control, hold time. If you hit control, it selects both columns. We also want to check where it says show two-sided p-value, because this question is asking for the p-value. And then when we click compute, it says the correlation between the number of reps and the hold time is negative 0.87. It's interesting that it doesn't print the letters R or P here, but that's exactly what these displays are saying, are showing. So this first number, the negative 0.87 number, is R, and then following that in parentheses is its p-value. I don't know why they didn't just write those there, but they didn't, so we need to know what they mean. Okay, so the R value for this problem is negative 0.87. I think it's fine to round to the nearest hundredth for this case. Negative 0.087. I didn't capitalize R automatically. Good. And the p-value, I think that was 0.002. Let me double check that. Yeah, 0.0022, which is 0.22 of a percent. 0.22 of a percent. Okay. Now, StatCrunch will find the numbers for us, but we need to explain what they mean. So let's do the one-dimensional test first. R. In this case, R is negative, but of course, to figure out if it's significant, we ignore the negative sign. 0.87 is its absolute value. Is that big enough to be significant? How do we know? How do we tell? We have to compare it to a critical value. In this case, there were 9 call centers. The number of pairs of data, N, was 9. So the critical value was 0.666. That's the number to beat. Did we beat it? Yes, we did. Okay, so we found that significant correlation because 0.87 is greater than the cutoff value of 0.666 from the table. I hope that agrees with the two-dimensional analysis of the p-value. Well, the p-value that we found is pretty small. It's much less than 1%. So in that case, there's also a significant correlation because p is smaller than any significance that we would normally use. It's less than 1%. And the significance values that we always use are pretty much always use are between 1 and 10%. Remember, if significance is not stated, we can assume 5%, 0.05, as a default. So hopefully these two statements should agree with each other. I think they pretty much always do. And that's how we show, that's how we run a formal hypothesis test for correlation. I just wanted to take one last peek at the lecture outline and draw your attention to something down here. If you're an advanced student, you might be a little bit curious about what this p-value really represents. A p-value is a tail area, but we don't know what it's a tail area of, right? So you might be wondering, like, is that the tail area on a normal curve, or one of those weird chi-squared things, or what is it? Well, it turns out that the sampling distribution is really complicated in this case. This p-value is in fact the tail area on a sampling distribution that is related to R, but it's not actually R itself. It's a t distribution, as it turns out, that is derived from R. But anyway, the math for this exact distribution is beyond the scope of this course. So we're going to have to be satisfied with knowing that we're using the same test as before. If p is small enough, then we've got a significant correlation. But as far as actually visualizing like what p is showing us, what curve it's measuring, we're going to have to not go into that much detail. All right.